Right now, about 400 kilometers above your head, a massive metal structure is falling out of the sky. Gravity pulls it down relentlessly, yet this falling object never reaches the ground. We find the explanation in the shape of the planet. Draw a straight horizontal line into space, and the Earth's surface continuously curves away from it. For every kilometer you travel horizontally, the ground physically drops by a measurable amount. Surviving gravity in space doesn't mean escaping its pull. It means moving in sync with the geometry of the planet below. Imagine standing up there and throwing an object perfectly horizontally at a slow speed. It moves forward for a brief moment, but gravity quickly pulls it down, and the trajectory arcs downward until it hits the dirt. Now imagine throwing it significantly harder. The faster projectile covers far more ground across the curve of the planet before gravity finally drags it back to the surface. This speed provides kinetic energy, the energy an object possesses due to its motion, which dictates how much of the Earth's curve the object can clear before it lands. If we push this physics experiment to its absolute limit, we can throw the object at an incredibly high speed. Eventually, you reach a threshold where the downward trajectory of the fall exactly matches the downward slope of the Earth's physical curve. The object is continuously dropping toward the ground, but the ground is dropping away just as fast. It is an eternal fall. To achieve this perfect synchronization, the object must travel horizontally at approximately 7.8 kilometers per second. This specific state of continuous falling has a name: an orbit. An orbit isn't a magical zone of zero gravity. It is a synchronization of extreme forward speed and planetary curvature. 300 years ago, Isaac Newton worked out these exact mechanics. He imagined a massive cannon placed on the peak of a mountain so tall it pierced the atmosphere. He reasoned that firing the cannonball slowly would drop it nearby. Firing it faster would land it further away. Firing it fast enough would send it completely around the globe without ever touching the ground. Today, Newton's 17th century thought experiment is playing out in low Earth orbit. The International Space Station is essentially a modern version of Newton's cannonball. It is a multi-billion-dollar machine locked in a state of inescapable freefall. Floating in space is simply the physical act of moving fast enough to fall forever and miss the ground entirely.